Hello, everyone. Welcome to the South Pole Safety Designing the NASA Lunar Rescue System Challenge webinar. Thank you for taking the time to join us today. Please feel free to say hello in the chat and let us know where you're joining us from. Our agenda for today will be to provide an introduction of our panelists, then an overview of the challenge, along with how to enter and submit your solution. And then we'll move into the Q&A. Please do submit your questions for the Q&A to the Q&A box on your screen. We may not get to all the questions on today's webinar. For those that we don't cover, we will look to respond to them via the challenge page, and we'll also be uploading a recording of today's webinar to the challenge page. So starting off with introductions, Amanda Rosansky, project manager with HeroX, and we're partnered with NASA to administer this challenge. I'm now going to pass it over to Katrine Morgan to begin the introductions of the panelist team.
Good afternoon, good evening, good day to everyone. My name is Katrine Morgan. I've been working at NASA for close to 30 years now. And here at Johnson Space Center, Houston, Texas, in the last 2 years, I joined the EVA and Human Surface Mobility Program Office. And in that program, I perform a technology integration function, and I do that for the center as well. Prior to joining EHP, our program, I did work for the International Space Station Program Office for close to 20 years, and I performed visiting vehicle integration for them. And then starting out, I was in the Space Shuttle Program Office, and I did cargo integration for them. So I'll turn it over to Anne next to introduce herself.
Hello, Hello, I'm Ann Vaughn. I moved over to EHP in the last year into the safety area, and I am currently the EHP crew survival lead. Before that, I spent some time in the station program office doing visiting vehicle integration, and before that, I spent many years as a flight controller in operations for space shuttle payloads and space station assembly.
Okay, go ahead, Tim.
Okay, I'm Tim Hall, and you'll notice a lot of us say we've been with EHP for just a couple of years because that's about how old EHP is as a program. I joined EHP right in the beginning about 2.5 years ago, and previously, well, in EHP, I am actually the Strategic Communications Manager, which means I handle all internal and external communication the program needs to have for things like this, for outreach, or everything from media to internal employee things. Prior to that, I've been at JSC for 30 plus years, and I'm an old mission control guy, worked in mission control as a flight controller. And as I grew up into management over there, I realized I really wanted to help tell the NASA story, and that's why I switched over to the communication side of things. So, and now I hand it over to, I think, Ben's next.
Yep. Hello, everyone. I'm Ben Green. I'm Deputy Manager for EVA Development here in EHP. I've also been at NASA for about 30 years, and for that 30 years, the vast majority of it has been spent in the EVA community, developing EVA tools and spacesuits. I've developed quite a bit of EVA hardware that, and some of it is still in use today on the International Space Station. And I help manage the development of the new Axiom spacesuit being designed for use on Artemis. So I'm very excited to see what this challenge provides for us to help us explore the moon more safely.
Jerry, go ahead and introduce yourself.
All right. Hello, everyone. I am Jerry Stevenson. I am the EHP Human Systems Integration System Manager. I also have been supporting EHP mostly from the beginning, so 2.5, 3 years now. My background is human factors engineering, and before I was supporting EHP, I was working in the human research program, supporting lots of studies looking at cognitive decision-making, just-in-time training for medical models for a crew, and also working on displays and controls for different vehicles. And I've been at NASA for 10 years, and before that, I was a U.S. Army combat medic. So happy to be here and excited to hear your questions and talk with you all. all.
Okay, Fiona, your turn.
Good afternoon, everyone, or good morning, depending on where you are in the world. My name is Fiona Kowiak. I'm a NASA flight director, so I work in mission control, leading our human spaceflight operations. I fly the International Space Station, and then I'm also our lead for lunar surface preparation. And so keeping our astronauts safe is one of the things we worry most about, and having good tools to do that. And so I'm really excited to get to see your ideas about how to do that safely, and looking forward to answering your questions today.
And last but not least, Steph.
Hi, my name is Stephanie Sipola, and I am the Deputy Manager for the EVA and Human Surface Mobility's Technology, Integration, and Partnerships Office. In this role, we have the opportunity to look at the technology challenges that haven't closed yet, looking for capabilities to solve the needs of the agency that the technologies may or may not exist or may not be flight ready. I'm really excited about this campaign. I'm excited to see what great ideas you all bring in. The innovation of the public is great and something that will prove beneficial as we solve this really challenging problem. I too have been here for going on 30 years. I started my career in operations as an instructor, teaching the astronauts how to build the space station, both mechanically and robotically. I've been a member of the EVA community for about 20 years now, and was a founding member of the program with the opportunity to formulate what it means to do technology integration and partnerships through the lens of a program manager. Happy to be here.
Great, thank you everyone for the introductions. We're now going to have Katrina Morgan provide an overview of the challenge.
Okay, once again, thanks for joining the webinar, and thanks for your interest in this very important challenge for us. So I'll try to keep it brief, because the main objective of this webinar, of course, is to answer your questions. But I just want to make sure we're all on the same page as far as what the details of the webinar, of the challenge are. So as far as a quick outline, I'll be stepping through a little bit of background. I will also talk through the challenge overview. Next, I will talk about the performance criteria. These are the must-have requirements and the nice-to-have features that we've outlined on the challenge site. And then I'll talk about the weighting associated with all of the criteria. And then I'll turn it back over to Andrew for Q&A. So as far as background, the initial Artemis missions will focus on lunar surface operations, science sample return, testing of new technologies for long-term lunar human presence, and gathering data for future Mars exploration. We've got some key aspects and parameters that the initial Artemis missions will have. So Artemis 3 mission is currently scheduled to launch in mid-2027. These early Artemis missions will take place in lunar daylight and near the lunar South Pole. This is a change from our earlier Apollo days. We do not have a baseline landing site location yet for Artemis 3. Right now, we're looking at 9 potential sites, but we should be baselining that really soon. And of course, it'll be at the lunar South Pole. The crew complement will consist of 4 crew members. All 4 will fly to cislunar orbit. 2 of those crew members will stay in orbit, while the other 2 will land and explore the lunar surface. The surface stay duration is expected to be about 6.5 days. We're looking at a total of 2 to 4 EVAs for Artemis 3 right now. We're looking at 4 EVAs. The total EVA duration will be anywhere between 4 and 8 hours, and that's pretty much limited by suit consumables. And then the excursions may take the crew away from their lunar lander as far as 2 kilometers. So this is going to be a key performance parameter that the design is going to have to live up to. And then these early Artemis missions also will not have any access to lunar rovers. Those will not come into play until Artemis 5 and onward. Artemis 5 will introduce our lunar terrain vehicles. These are unpressurized vehicles And then Artemis 7 will introduce the pressurized rover that JAXA Japan is building. And next slide, please. So more on background. So EVAs historically have been considered one of the top 3 risk events in human spaceflight, which is why, we're really working safety aspects of that. And so during a lunar EVA, there's a possibility that one of our 2 crew members could become fully incapacitated. And what that means is that they're not able to help themselves. They're going to be fully dependent on their buddy to help them back to safety. And so full incapacitation can be a result of a spacesuit hardware failure, or a crew physical injury, which is caused by fall, decompression sickness, or any other illness for that matter. And so because of all of that, it's really important that we have thorough planning, we have flawless execution, and we really look at proactive implementation of risk mitigation strategies, including assistive systems and tools. And so this is where this challenge comes into play. We're looking for that tool to make sure that our crew members can return to safety. And so we're really excited to engage you guys, and we're really interested in seeing all your innovative and forward-thinking ideas to help solve this very important challenge. Next slide, please. So this is more details about the challenge itself. The problem that we're trying to address is the South Pole presents us with some pretty extreme challenges. First up, we have a very rugged terrain, and I'll provide more specifics about what that terrain looks like. We're dealing with some huge temperature fluctuations. We have very low angle lighting, and we also are in a reduced gravity situation. And all of those challenges make the risk of having a fully incapacitated crew member more likely, actually. So what we're looking for is a rescue capability that would allow a single crew member, this is our healthy crew member, to transport a fully incapacitated crew member across the lunar surface up to 2 kilometers away from the lunar lander without relying on a lunar rover. And one of the parameters is, is that the fully incapacitated crew member could be up to 755 pounds. This is terrestrial weight. There's been several questions in the campaign so far where folks are asking about what mass means. And so all of our mass parameters that we've outlined are terrestrial weight numbers. So the specific challenge is to create a compact, efficient system for astronaut rescue on the lunar surface, helping ensure a swift, safe evacuation in extreme conditions. So you all have an opportunity here to play a vital role in enhancing the safety measures of our future lunar explorers. Next slide, please. So now moving on to the lunar specific challenges and some of the specific parameters associated with those. When we talk about extreme temperature variations, we're looking at sunlit areas that could reach up to 130 degrees Fahrenheit, and shaded areas that could drop down as low as negative 334 degrees Fahrenheit. We're also looking at poor lighting, the low angle sunlight, and long shadows. And so the sun angle could be anywhere between 2 and 7 degrees above the horizon, depending on the time of year. And what that translates into is that your shadows could be 27 times as tall as the actual height of the object. So this is where things get really interesting looking when you're on the moon, and it could lead to some the crew not, really understanding what they're seeing on the moon. The lunar terrain is also very rugged. The rocks can range anywhere from 15 centimeters up to 20 meters in diameter. Craters could range from 1 to 30 meters, and the slopes could be up to 20 degrees. And these are slopes that could be either up, down, or cross slopes. The lunar gravity is also 1/6 of Earth's gravity. Next, we have lunar dust. I'm sure if you've done a little bit of research that you've seen that a lot of the Apollo crews expressed issues with lunar dust, and so it's also known as regolith, and this lunar dust is extremely sharp and electrostatically charged. So this is something that you've got to consider in your design as well. And then finally, there's the lack of atmosphere. This is pretty high level. For those of you that are interested in getting more details, we did make a copy of the Disney available to you. This is where the details of our natural environments on the lunar surface are documented. And those are available in the resources tab on the site. Next slide, please. So as far as temperatures, this is something you want to consider for equipment and suits. So you want to make sure that your hardware is able to function within that wide temperature range. The unique lighting conditions, this represents navigation challenges and may impair depth perception of the crew. And as a result, it could increase the risk of falls. Traversing rugged lunar terrain requires careful planning, but when you think about it in your design, you want to make sure that your design is robust enough to be able to handle those large rocks and craters and everything else. Lunar gravity, what that's going to do is it's going to affect mobility and object handling. So inertia is something you want to consider in your design too, because it may impact movement and manipulation of the equipment. Lunar regolith could damage equipment or impact movement. And so since it's so fine, it's something you want to consider in any mechanism that you consider in your design solution. You want to make sure that it doesn't get stuck in there and either hinder performance or prevent movement altogether. And then lack of atmosphere, this is more of an issue for crew members as it introduces them to solar radiation and also micrometeoroid impacts, perhaps not as much a challenge that you need to consider in your design itself. Next slide, please. So performance criteria, so the list that you see on this slide, these are our must-have requirements. At the very top, we've got low mass and minimal volume. This is going to be our key criteria that we're going to look at in or one of our key criteria that we're going to look at in our judging process. And so we've asked for you to aim for a total mass of 23 kilograms or 50 pounds. Again, this is terrestrial mass. We understand that this is a very sporty number, but we just ask that you get as close as possible to that, since whatever mass you come up with, this is mass that we will need to launch to the moon, as well as, this is mass that the crew members will have to haul around on the lunar surface. So that's why it's such a big deal. We're also looking for something that's effective and safe for transportation. Again, it's something that needs to be able to travel a range up to 2 kilometers and up to 20 degrees in slope. We're looking for something that's easy to deploy and use. And really what that translates into is time. So we want something that's easy to assemble, whether it be in the initial assembly or the final assembly when you actually have to use the tool for a contingency. So, time is precious. We only have so much consumables, so we need something that's a quick deploy. Compatibility with lunar environment. I think I've talked enough about that, but really we're looking for a design that can handle all of those extreme environmental constraints that the moon will introduce. And next we have safety and reliability. So reliable is obviously key. We want to make sure that it's something we can depend on should we have such a contingency. And then safety, we want to make sure that your design solution doesn't impact safety. So things like sharp edges that may puncture the suit or anything like that, that's what this is trying to achieve. And then finally, we're also looking for minimal impact on suit design. We have shared that there's some attachment points on the suit, which your concept can utilize, but we don't want much more beyond that in terms of impacting the suit, since that's currently under development by Axiom. Next slide. This is a list of nice to have features. So we're looking for something that's collapsible and has efficient stowage. This is mostly for upmass reasons. We want to make sure that we limit the real estate that it will need to take up in our landers. Adaptability, anything that can adjust to different mission requirements, that would be a nice to have. Anthropometric accommodations. It would be ideal if your tool can accommodate a wide range of crew members, but if it can, that's a knob we can turn once we select a design. Ease of manufacturing, again, ideal, and especially if you consider when Artemis 3 is launching, we want something that we would be able to produce and have ready for flight pretty quickly. And then multifunctionality is another nice to have. And then the last slide is our judging criteria. So we've got 3 categories that we'll be looking at. Innovation is first up. That's given a total of 20%. This is because we're looking for your really creative ideas here. Think out of the box type of ideas. And so that'll be graded pretty highly. Performance requirements, those must-have requirements, they total 55% of the total value, and massive volume is our top priority there at 17%, and then the nice-to-have features total of 25%, and then you see them the allocations there. And that's really all I had in terms of an overview. So I think at this point I'll turn it over to Andrew to start the Q&A.
Great. Thank you, Katrine. Appreciate that. I'm going to just take a quick moment just to show us the challenge page. So I'm going to switch over a share here and just show everyone. So this is our challenge page. You can find it at HeroX/NASA Self-Pull Safety. This will give you all the information on the challenge. So under the summary tab, it's going to give you the overview and the guidelines. It's all the information you need for the challenge. Additionally, we have the timeline. Do want to point out we're now 2 weeks out from the submission deadline. So for those of you that haven't submitted, just a heads up, you've got 2 more weeks to get your submission ready. And then just wanted to share, you could post any questions you may have to the forum. The updates is where we'll be sharing the recording of this webinar. And then just a reminder that there are these additional resources which are linked to from the guidelines to help to give you some more information on some of the key areas of the challenge. I'm going to stop share. All right, and now we're going to get into the Q&A portion of our webinar today. So I'm going to get into the questions here. All right, so let's get started. Are the dimensions of the portable life support system on the astronaut's back available? That's our first question.
Okay, I think I'll take that one. So while we can't provide very specific dimensions of the portable life support system for several reasons, the sensitive nature of the specific design is one, but also the exact dimensions, the precise dimensions are still potentially in flux. We're still working on the design of that spacesuit, and so it's very possible that those overall dimensions change over time as we realize that we need to make changes in order to meet our objectives. And so what I can do, though, and I did put some thought into at least giving you a frame of reference that would give you an idea of the size of what we're dealing with here. So I have a handy model of this is what we call the government reference design. This is the exploration EMU, or the XEMU, that the government got to what we call a preliminary design review, almost a critical design review of this design. So while this is not exactly the way our lunar suit that we're in development now will look, it is very similar. And so you will see this. And so for those that aren't familiar, this is the portable life support system on the back. This is the system that provides cooling to the crew member, pressure, oxygen, everything to keep you alive, recirculating, taking out carbon dioxide, keeping the crew cool or warm, whatever that may be. And so the question about what is the size of the portable life support system here, tried to come up with a frame of reference that across the world everybody would understand, which wasn't all that straightforward. What I came up with, and this was fairly contrived, so apologies if this isn't very clear. We all travel, and so I think a lot of us prefer to take carry-on bags on a flight. And so what I would say is if you had 2 maximum size carry-on bags that you rolled up to the counter and you set them on their side next to each other, that's about the size of this Pliss from all different dimensions, approximately. And so the carry-on limit in the United States and internationally, I think they're off by about an inch or so. But again, those precise dimensions I don't think are critical to our task here, but that's about what we're talking about.
Thank you, Ben. That's a great analogy. All right. Another suit-related question. Are there attachment points on the rear of the suit?
And so, yes. And so I'm going to refer to my handy model here again. And so there are 4 total attach points on the rear of the suit. And so those are also located on the portable life support system. So specifically, there are 2 interfaces on this side and 2 interfaces on this side of the Pliss, and they are accessed from the rear. And so we use those attach points to mount the spacesuit against the wall of the vehicle for launch and landing. And so those attach points are fairly strong. So they're strong enough to withstand or take the load of a full spacesuit and a crew member in Earth gravity. And so if you're using those attach points to either lift or drag the crew member in the suit, those attach points, assuming you're using all 4 of them simultaneously, should be sufficient to perform your task.
Excellent. All right. What orientation is possible for transport, like vertical, horizontal, as examples?
I think that one's going to go to me. So there's a few different types of positions that you can consider that are possible for not only transport on a vehicle or whatever method you might choose, but we also need to consider ingress, egress, loading and unloading into a vehicle. So what we've come up with here is to, first of all, I'll tell you what the don'ts are. We don't want to put the crew member on their stomach lying prone, and we don't want to put them upside down like they're doing a headstand. Those are positions that you can imagine are probably not the best for helping a crew member who might be experiencing a medical event, such as difficulty breathing and maybe some cardiac issues. And so what you want to do is to put them in a comfortable position. What we recommend are the 2 positions, such as we call them the Fowler's position and the semi-Fowler's position. So that's FOWLERS, Fowler's position, and semi-Fowler's. So that's at and I'm going to look this up. It is the reclined angle, and it's between 30 to 60 degrees from horizontal. We want their legs stretched out in front of them, flat. And then if they were to be transported, let's say you had them on a vehicle, you could have them sitting straight up, and you could also have them standing. But you need to consider the different medical situations that they might be experiencing. So another thing that you need to consider, as Ben was just showing, the Pliss, if you had a crew member in their suit, oh yes, thank you for Vanna whiting it for me. If you had the crew member sitting with their legs outstretched, if they were to try and lean back, they would be hitting that Pliss behind them. So you might be constrained by that position. And I believe those are the things that you want to be able to consider, their comfort and the medical conditions. You want to be able to visualize them to make sure that they are breathing and that they are not experiencing any adverse effects by the position that you put them in.
Great, thank you. Next up, will the device be continuously carried or only retrieved when needed?
I can take that one. We do expect the device to be with the astronauts during their spacewalks. As mentioned in Katrine's presentation, the astronauts may be up to 2 kilometers away, and we don't want them to have to go back to the lander, get the device, and then come do the rescue. I do want to point out the questions asked about it being carried. It's pretty difficult to have things that the astronauts are, carrying in their hands, for example, for the whole spacewalk. And so when we say we expect the device to be with them, we envision that it could be on kind of a transport device that the rest of their tools are on, or if the device itself could be pushed or pulled or attached somehow. And so we do expect it to be with them, but I don't want people to get too stuck on carried, because our goal, right, would be that the astronauts don't have to use their hands on the device at all times to carry it, and can have it on some kind of transport system that moves with them.
Great, thank you. And that kind of leads into our next question. Will crew members push a tool cart through the EVA? If so, may the system be carried on the tool cart until deployment?
Yep, I'll take that one too. Definitely related. We do expect the astronaut will have some kind of transport device. So when they're going up to 2 kilometers away, they're going to have tools with them that they're going to use for the science they're doing. They may also have a payload or something like that. And then they'll be collecting moon rocks, and so they'll have sample bags. And so we expect there to be some kind of device that that all gets carried on, and absolutely that we are open to the rescue device also being on that same kind of transport.
Excellent, thank you. Okay, so we have more of a design-related question here. Can the solutions include wheels, batteries, motorization, and/or be autonomous?
Okay, I will take this one. So the challenge does not preclude any solutions within these spaces. So if you want to include batteries or motors, wheels, autonomy, however, we recommend that you balance those additions against the performance parameters, and you will have to go through trade-offs on what the solution is against the performance parameters.
Excellent, thank you. And what is the preferred lubricant for moving parts on the lunar surface?
So I'll take that one. So it is possible to utilize lubricants in space hardware. There's lots of different types of lubricants you could choose from. There's dry film lubricants, greases, oils. We frequently use Teflon coated parts, or even Teflon itself as a bushing. While there is no preferred lubricant, there's not one lubricant that we use in any one particular application. The important thing you have to consider is that whatever lubricant you choose has to be compatible with the environment. So on the lunar surface, in the areas that we're planning to go, it's going to get very cold. And so greases and oils typically will freeze in the temperatures that we're talking about. So unless you're providing a way to keep those specific types of lubricants warm, which we do in the spacesuit, we use lots of lubricants in the spacesuit, then that might not be your best choice, for example. So there's really not one specific solution. So the question presumes that there's one that we can advise, and there really isn't. We use lots of different types of lubricants, but as I said, you have to make sure that whatever you choose is compatible with your environment. You also have to consider that the lunar surface, obviously, what we're dealing with is a very dusty environment, and so if you do choose to use a liquid lubricant or a grease, that you protect those mechanisms from dust getting in there as well, as that will really cause bad abrasion and give you problems with your mechanisms. So all those things need to be considered in your lubricant selection.
Great, thank you. All right, is there information available on how lunar dust affects materials such as metal, plastic, or rubber?
and I'll tackle that one. Yes, there were references included with the challenge, and because of the number of questions that came in on this, we have an additional list of references that we will share on the website following this webinar.
Excellent, thank you. Next up, how does NASA view the role of autonomy and AI in aiding or complementing human decision-making for a lunar rescue system?
Background.
You're on mute.
Okay.
Oh, there we go.
I'll take this one. This was an intriguing question. So I want to remind the team that this task, the ICR rescue task, does require human strength. And so the challenge itself is to design hardware to facilitate a healthy crew member rescuing an incapacitated crew member. And however, the question about AI, if a team can come up with a way for AI to help facilitate that rescue, there's nothing in the challenge that precludes that. We just want to make sure the team fully understands and focuses on a hardware design implementation that allows the rescue of the crew member. And if there are innovative ways to use AI in helping getting that crew member back, then we're open to that in the solution space.
Excellent, thank you. All right, the next question, is there information available on preferred materials NASA uses for spacecraft?
Yeah, so I'll take that one. So this is very similar to the question on lubricants. The answer really comes down to the specific application that you're needing a material for. So we use hundreds, if not thousands, of different materials for different applications of spaceflight hardware. So similar to lubricants, you really need to choose the material you want to use based on its ability to meet your requirements and be able to last in your environment. So because it's such a wide question, and again, it presumes that there is a preference there. We really can't provide. There's so much information to provide there, and a lot of it, from a materials properties perspective, is available on the internet. I guess what I can say, that help I can provide, is, generally speaking, for structural materials, we use a lot of different types of aluminum. When we need stronger materials, we tend to lean towards stainless steels. Sometimes we use titanium in specific applications. We sometimes use carbon fiber composites. Are very strong and lightweight. But outside of metallics, we also use a lot of non-metallics and polymers like PEEK. It's a polyether ether ketone, I think. There's Vespel and other polyimides that we use quite a bit, like Kapton. Again, I mentioned Teflon. We use Teflon in a lot of different locations. So there's really no one magic single material for space flight. Like I said, we tend to use a lot of aluminums, and those material properties should be readily available in lots of textbooks and on the internet.
Excellent, thank you. All right, next question. Why did NASA choose the South Pole?
So this is a great question. I'll take this one. So I think the answer here is twofold. First, the South Pole has an abundance of resources. This includes both usable minerals and metals in its permanently shadowed regions, also known as our PSRs. And these resources will be key to extending our missions, building an infrastructure on the moon, encouraging further exploration, and also to promote lunar commercialization. So that's kind of the first answer. And then, of course, there's the scientific perspective. The South Pole presents us with a perfect recording in time, and that terrain is some of the oldest terrain on the moon. And so we're hoping that it holds the answers to some of our fundamental questions and mysteries of the moon and the universe as a whole. So that's the answer.
Great, thank you. All right, next question, and we're getting close to time, so we'll have time for just a few more questions here. And just again, a reminder: anything we don't get to today, we'll make an effort to answer all of them on the challenge page as a follow-up. If the design uses fuel, is it included in the 23 kilo weight limit?
Can you repeat that question again? I'm sorry.
Sorry, Katrine, if the design uses fuel, would the fuel be considered in the 23 kilogram weight limit?
Yes, it would be. Anything that's part of the design that contributes to that total allocation of 50 pounds.
And let me add to that also. There was a discussion earlier about batteries. We would also need to account for if you are bringing batteries, they probably need to be recharged. So we also need to consider that any equipment that needs to be brought along to recharge those systems also needs to be considered.
Great, thank you. Here's another question. Can the design be split into two parts, with one astronaut carrying one part and the other carrying the rest?
Sure. I mean, if we're talking about during nominal operations, yes, I think the design could be split and then fully assembled in the event of a contingency. And then, of course, it's only one crew member using it at that time.
Great, and we do have a few more questions about just the attachment points. I don't know if Ben, maybe you just want to share a little bit more about what those, how those could be used, or what they might sort of end up looking like or functioning.
Let's see. I cannot provide specific, detailed dimensions of the interfaces. Again, the sensitive nature of that design kind of precludes us from providing those specifics. I think for the purposes of the challenge, I would just assume that it is possible to develop an attachment point that would allow you to lift or drag, and that level of detail is something that we can work out once the concept has been provided. So, like I said, we use those points to mount the suit against the wall of the spacecraft. So during launch, we have launch loads or accelerations and decelerations in every orientation. So those attach points have to hold it in place in all directions, right? And in torsion or in torque. So I would say just, the very specifics of the interface aren't as important as just understanding its capability. And again, those attachment points, assuming you use all four of them, are very strong and can handle the weight of an entire spacesuit and crew member in Earth orbit. So, remember, you're going to be in Earth gravity. You're going to be in lunar gravity, which is 1/6 of that. So if you're planning to drag or lift the entire assembly using those points, it should be adequate to do so. And I understand that in the package we provided, the details about these lifting points, the fact that they existed, or these load points were not in that package, and we can provide that update.
Excellent, thank you. Well, we are at time now, so I do want to say thank you to all of our panelists. Thanks for taking the time and answering the questions for us today. And thank you to everyone else who was able to join. Thank you for sharing. I know there are a number of questions we didn't have time for today, but we will make an effort to answer all of them for you on the challenge page. I just wanted to share a reminder that the submission deadline is February 6th, so there's another couple weeks for you to get your submissions finished and submitted. We will be uploading a recording of this webinar to the challenge page. So thanks again, and have a great afternoon or evening wherever you may be. Thanks, everyone.
Bye.